Hello, my name is Jonggyu Park. I'm from Sungkyunkwan University. Today I'm going to talk about the fragmentation problem on flash and obtain storage devices and a new solution to address the problem. Fragmentation is a phenomenon where file blocks are scattered across multiple non-contiguous areas. It is commonly called as file fragmentation, file system fragmentation, and file system aging. Traditionally, we believe this significantly degrades the I/O performance since it increases the seek time of the underlying storage devices. So what we can do is performing defragmentation like this. However, conventional defragmentation tools have several drawbacks. First, the conventional tools are designed for storage devices that have seek time. Therefore, they migrate the entire contents of data, which significantly degrades the performance of current running applications. Second, modern storage devices have a limited lifespan. Therefore, the additional bulk writes incurred by defragmentation, it reduces their lifetime. Finally, it is really time-consuming. Therefore, people are afraid of using defragmentation. First, let's find out why fragmentation degrades I/O performance on flash and obtain storage. Suppose that a process issues a read operation. In the file system layer, file systems investigate the sequentiality of LBA of the read operation because file systems view data in terms of LBA, whereas applications handle data using file offset. If they are not sequential, request splitting happens. Here, request splitting means a single system call is divided into multiple I/O requests. The problem of request splitting is that it increases the number of I/Os and makes the I/Os smaller and increases their randomness. This significantly affects I/O activities throughout the entire I/O stack. Afterwards, the I/Os experience the block layer, which performs request creation, queue insertion, and various other activities. And then, the I/Os are transferred to the storage through I/O interfaces, and finally, the corresponding data will be fetched from the storage chips. SSDs utilize multiple parallel units to maximize I/O performance. However, fragmentation decreases the size of I/Os and increases their randomness, which hinders efficient utilization of internal storage resources. Like this, fragmentation increases kernel overheads, interface overheads, and resource conflicts inside the storage. To verify request splitting is the main problem, we perform some experiments. Here we utilize new terminology, frag size and frag distance. Frag size denotes the size of each fragment, and frag distance means the distance between two fragments. We executed 128 KB sequential reads on FTF file system while varying frag size and frag distance. Here, since the request size is 128 KB, request splitting occurs only when frag size is smaller than that. In the case of hard disk drives, the performance is sensitive to both frag size and frag distance. A longer frag distance means hard disk drive requires more time locating its mechanical part on the corresponding location. On the other hand, none of flash obtained storage is sensitive to frag distance because they do not have seek time. Instead, they are sensitive to frag size until the frag size becomes a request size, and the performance gain gets smaller after that. This means request splitting is a critical factor to the performance of modern storage devices. From these experiments, we can guess that the performance of modern storage devices mostly depends on the occurrence of request splitting and is irrelevant to the distance between fragments. To mitigate the problems of conventional defragmentation tools, we propose a new defragmentation tool for modern storage devices. First, we now know frag distance is not important to the performance of modern storage devices according to the previous experiment. So let's just ignore frag distance and do our best to prevent request splitting. So what we want to do is this. Let's partially migrate certain data, not all the data. But the problem is, we need to decide which data to migrate and how to migrate. To find out the optimal pieces of data for migration, FragPicker performs I/O analysis. Additionally, FragPicker utilizes some techniques to perform file system agnostic migration while minimizing the amount of writes. To achieve this, FragPicker consists of two phases, analysis phase and migration phase. In the analysis phase, FragPicker monitors the system call layer and extracts necessary information using BCC. BCC is a toolkit for efficient kernel tracing, making use of extended Berkeley packet filters. Using BCC, we extract various information such as request type. Afterwards, FragPicker performs per-file analysis. In this process, it creates profile range list, which includes start of set, end of set, and the I/O count for each range. This process also merges overlapped I/Os and updates the I/O count. Without the merge process, the overlapped I/O ranges can incur another fragmentation after migration, like this. Therefore, we merge such ranges like this. The hotness filtering truncates the file range list according to the hotness threshold. In the profile analysis, FragPicker calculates the I/O count for each range. Using the I/O count, FragPicker only remains hot data regions that are frequently accessed. In other words, this process removes unnecessary pieces of data that are not critical to the performance. The migration phase utilizes the profile range list that are obtained from the analysis phase. First, FragPicker performs fragmentation checking towards each chunk in the file range list. Here, the chunk 1 and chunk 4 are fragmented, so they need migration. However, the third one is actually contiguous, so migrating it creates unnecessary writes without any performance gain. So, FragPicker keeps this as it is. Like this process checks the fragmentation state of each range and decides which one to migrate in order to further minimize the write amount. Next, FragPicker performs block location. In the case of in-place update file systems, explicit block location is necessary for data migration. Therefore, using fallocate, we allocate a new contiguous area in advance to actual migration. Here, since outplace update file systems do not require block location, FragPicker can skip this process in that case. Finally, data migration is performed using user-level I/O libraries. After defragmentation, performance-critical data become contiguous, and I/Os towards such data will not cause request splitting. Since the chunk 2 is not on the file range list, we think the data are not performance-critical. Therefore, FragPicker does not migrate the data. To evaluate FragPicker, we use two different kinds of SSDs, one for flash and one for Optane. First, we generate fragmented files, execute various workloads using the files, and measure the I/O performance. Afterwards, we perform defragmentation, calculate the amount of writes for defragmentation, and measure the I/O performance again. In these experiments, we want to know if FragPicker can really reduce the amount of writes for defragmentation, and if it can achieve a similar level of performance gain compared with conventional tools. We utilized three different kinds of major file systems and their defragmentation tools. The experimental results show FragPicker actually does reduce the amount of writes for defragmentation. In the case of sequential I/Os, FragPicker shows around 50% less writes and 75% less in the case of stride workloads. This reduction in the amount of writes is because the analysis phase of FragPicker effectively finds out the optimal pieces of data for migration, and fragmentation checking of the migration phase further minimizes the unnecessary writes. In terms of performance, FragPicker improves both sequential and stride performance by around 30% and 42% after defragmentation. And in the case of stride reads, FragPicker even outperforms the conventional ones. FragPicker migrates the fragmented data in the way the data are actually accessed. Therefore, FragPicker can place the data in a better way than migrating the entire contents in a sequential manner. In the case of Optane SSD, FragPicker could achieve around 120% performance improvement at most. It is because Optane SSD is high-performance storage, and the additional kernel overhead caused by request splitting is more noticeable. Here, in the case of sequential reads, the performance gap between FragPicker and E4 Defrag shows only around 0.1%, while FragPicker reduces the amount of writes by approximately 50%. More experiments including database and file server workloads can be found in our paper. In conclusion, FragPicker is a new defragmentation tool for modern storage devices. Thanks to the existing tools, it requires no kernel modification and is file system agnostic. FragPicker requires the systems to support eBPF, file system level consistency, fallocate, and the file frag program. Finally, it needs the file system ability to provide a contiguous LBA reason for a single write operation, since FragPicker relies on user-level I/O libraries for data migration. Thank you for listening to our presentation. The source code of FragPicker is available here. If you have any questions or suggestions, you are welcome to contact us.